Right, so what we're going to do now is look at an example of a simplex algorithm applied to one of the problems we looked at in the labs, and that is the window glass problem, where we have to make batches of doors and windows subject to particular constraints. So you might recall this window glass, and the problem is, or the decision variables are, the number of batches of doors and the number of batches of windows. And I'll call those decision variables X and Y. What we have is 3 factories, and in each factory a total number of hours available to us for doing the doors and windows in. So let's just write up a resource table. So we have the 3 factories, F1, F2 and F3. In factory 1, there's only doors are made and we have 4 hours available. In factory 2, only windows are made. They require 2 hours each for a total of 12 hours. And in factory 3, let me remind myself, doors require 3 hours, windows 2, for a total of 18 hours available. And the profit, recall, I'll call that Z for the profit, is again 3 hours for $3,000, I should say, for doors and 5,000 for windows. So what we're going to do is turn those into inequalities, and then from that create an initial simplex tableau. So first the inequalities, they look like this. We can just write them directly from this resource table. We've got x less than or equal to 4, 2y less than or equal to 12, 3x plus 2y less than or equal to 18, and of course the profit z is 3x plus 5y. So what I'm going to do now is take those inequalities and turn them into an initial tableau of our simplex algorithm. So now that we have the inequalities that describe the problem and the function that we're trying to optimise, the objective function, now we have to turn them into equalities for creating the initial tableau, which means we have to introduce slack variables. In this case, there are 3 inequalities or 3 constraints, so I'll have 3 separate slack variables. So the first inequality, which as you recall was x less than or equal to 4, will become x plus s equals 4. The second inequality, which was 2y less than or equal to 12, will be 2y plus t equals 12. And the final inequality, which let me remind myself was 3x plus 2y less than or equal to 18, will be 3x plus 2y plus u equals 18. Then of course we have our function for or equation for the objective function, which will be z minus 3x minus 5y equals 0. So now we turn all that into an initial tableau. So there'll be a number of lines in it. So let's have x, y, s, t, u, and b for the final right-hand side. And now we can just read across. So 0, 1, 0, 1, 0, 0, 4. And as you can see, what I'm doing there is simply copying down the coefficients from the equation that we have. And the second one will be 0, 0, 2, 0, 1, 0, 12. Final is third inequality. The third constraint will be 0, 3, 2, 0, 0, 1, 18. And finally, for the objective function, 1, minus 3, minus 5, and a whole lot of zeros to finish. So there's our initial tableau. Now we're going to do several things with it. The first thing we're going to do is to try and find the pivot, which as you recall is the element around which we do all our computations. And we start off by trying to find the element in the bottom line, which is the most negative. In this case it's minus 5. So that column there, the y column, will be our pivot column. What we do now with that column is to divide the non-zero elements into the values of b. 12 divided by 2 gives us 6. 18 divided by 2 gives us 9. and 6 is the smallest number of those two, so our pivot value is 2. What we'll do next is the operations on that. We will turn the pivot value into 1 and apply row operations to make everything else 0 in that column. So the first thing we do, as you recall, with the pivot row is divide that by the value of the pivot. The value of the pivot is 2, so after dividing by 2, let me write this up, we have z, x, y, our 3 slack variables, and the final result. The top line stays fixed, that was 0, 1, 0, 1, 0, 0, 4. The next line contains the pivot, so that's the line that we divide by the pivot value, which was 2. So we end up with 0, 0, 1, 0, half, 0, 6. And the bottom lines just copy down as they were. 3, 2, 0, 0, 1, 18. And of course the value of the objective function. So there's the pivot row that we've divided by 2. And there is the pivot value, which is now 1. So the next step is to get zeros everywhere else in that column. And to do that, we need to subtract or add to rows 3 and 4 multiples of this row 2. So let's just do that. We'll just write this table up again. Now, happily enough, we don't have to do anything in the top row because there's already a 0 there. That's the nice thing about this sort of problem, which already has zeros in it. The second row we don't have to do anything with because we've already done it. There's our 1 there that we're going to work with. And it's the last 2 rows we have to deal with. So to get a 0 there, we use that value to subtract that number of copies of row 2. So it'll be row 3 minus 2 row 2. And if we work our way across, we'll get 0, 3, 0, 0, minus 1, 1, 6. And at the very bottom, it'll be row 4 plus 5, row 2. So we'll have 0, negative 3, 0. And you see at this stage, we've got now zeros everywhere in the y column except for the 1, which was the pivot place. 0, 5 on 2, 0, and 30. So this completes the first iteration, or the first update of the Simplex Tableau. At this stage, we have, well, that should be a 1 there. We have the y value of 1, so it's like we're making batches only of windows. And because we're selling 6 batches of windows at a profit of $5,000, giving us $30,000. So that's certainly not optimal because there's still a negative value in the bottom row. But we'll update that by working out where the pivot is for the next iteration. We can do that very quickly now. So the pivot will be obviously in that column because that's got the most negative. We will be dividing the non-zero values in that column there over here. 4 divided by 1 is 4. 6 divided by 3 is 2. That's the smallest value, which means that this will be the pivot for the next operation. So we're going to do exactly the same thing again, but with this tableau to start with. We'll be dividing this pivot row by 3 to get a 1 in that position. And then we'll be subtracting appropriate multiples of it to get zeros where there are non-zero values in that column so far. So now we continue, we do exactly the same thing again in terms of updating the tableau by dividing the pivot row by the pivot and then row operations to get zeros everywhere else in that column. So we'll try to do this fairly quickly. Try and squeeze 2 columns in or 2 tableaus in. So in this case it was the third row that was going to had the pivot, so the first 2 rows will be unchanged. There's the first row. The second row is the row that had the original pivot in it. And the third row is the one we divide by the pivot value, which was 3. And when we do that, we'll get 0, 1, 0, 0, minus a third, 1/3, 2. And the final objective function row stays as it was before. So recall that now our pivot is this element here. So this is the one we're going to change to have zeros everywhere else in that column. So again, very quickly, we'll just write up another table, squeeze it all in. So here the first row will have the third row subtracted from it. And if we do that, we'll have a whole lot of zeros. The second row already has a 0 in it, which is nice for us. We don't do any work for that one. The third row is our pivot row, so again, we don't have to do any work there. And the final row will be row 4 plus 3 row 3. And when we put that in, we'll have 1, 0, 0, 0, 3 halves, 1, 36. And now we know we've reached the end of the simplex operation because there are no further negative values in the bottom row. And from this we can read off the x and y values. We can read off y equals 6. We can read off x equals 2. And we can read off the maximum or optimal profit, which is 36. And as a bonus, recall, we have the shadow prices for the binding constraints given in the bottom row. So that completes the simplex algorithm for that particular problem.